Aspectoro, hello. Okay, I don't know where he is. Anybody wants to volunteer for recording this session because I'm on my work laptop and I can't record.
Yeah, I can do. Let's. Okay.
Oh, okay, you're recording. Okay, perfect, great. Okay, great. Let's get started. If anybody wants to turn on their camera, that would be amazing because I am feeling bored here, seeing only myself. Oh, thank you. Oh, that's great. Okay, perfect. Okay, guys. So, welcome back to Quantum Mechanics Group Study. My name is Oggy, or you can call me Sid, doesn't matter. Last time we did up until the sequential Stern-Gerlach experiments, right? Is anybody new here who wasn't here the last time?
I'm I just
You?
joined.
Okay, yeah. So I hope you like studied up until Stern-Gerlach, like sequential Stern-Gerlach, because we're gonna start from there. I'm gonna give you a summary, but like we're not gonna discuss the whole thing.
Okay, thank you.
Yeah, you studied it, right?
I did, but I'll check it up.
Okay, no worries. It's a simple experiment. It's not a very hard experiment, I think, and it displays the properties of quantum mechanics very well. So once we start, and like I think we should, and we have. Never mind. Okay. Anybody wants to volunteer giving the summary, or should I? Okay, I'm gonna wait for like 5 seconds. Nobody? Okay, cool. I'll just give a short introduction to or a summary to what we did the last time. So, we started with the book by J.J. Sakurai. It's called Quantum Mechanics or Quantum Mechanics and Applications, something like that. The book is in our Discord chat under the study group channel. So the first thing that we started with was not a lot of the historical developments like Planck's radiation law and Debye theory, Bohr's atom, etc. Right? We started with the Stern-Gerlach experiment. Now, as you guys can see my screen, I'll just explain it a little bit. So here on the right is a furnace, right? In the furnace are silver atoms, which for their particular property that they have one electron in their outermost shell. Because of that, they have been chosen, right? When they are heated up, they are released from the furnace and they go straight into the magnetic field under this magnet. The magnetic field is inhomogeneous, right? And as we can see by classical prediction, we would have predicted that there would have been a continuous result on the screen, continuous distribution. But what was actually observed was that there were only two positions on the screen where the atoms collided. So that is weird, basically. It defies the classical predictions. So we question them and we come up with we came up with the term of we discussed it was the spin, right? Quantum spin, right? And it is what results in these two positions on the screen. I okay, that's the best explanation I could give. Anybody wants to add anything to that, I would be grateful. Okay, I think we are good. Nobody wants to add anything. So that means hopefully this is clear what's going on here. We did the description of the experiment that I've basically explained. This formula, this is coming out from the EM book, electromagnetism, right? We're describing the force, and the force is what results in the silver atoms to be deflected from their standard trajectory. However, as we can see, there is mu and there is minus mu. But yeah, so instead of continuous values, we get positive half and negative half, like minus h by 2 and minus h bar by 2 and minus and plus h bar by 2, something like that. Still, like that's actually not written here, so I'm just making that up. But anyways, okay, we are gonna move on to sequential Stern-Gerlach experiment. And anybody wants to read first? Any volunteers? No? Okay, guys. One thing that I forgot to explain is that this is a group study. If I am the only one talking, then this is not a group study. This is a lecture, and this is not a lecture because I cannot give a lecture on quantum mechanics. I barely know the stuff myself. I'm here to learn. Everybody else is also here to learn. So we should try to learn together, I think. So like people should participate. There should be discussion, and especially the reading part. Like I'm not gonna do all the reading. I'm hoping that we will, like everybody will read a little bit one at a time. That will keep you interested. You won't fall asleep, and that's the whole point. Like we actually learn here. So any volunteers? Yeah, people are
Okay,
sleeping.
let me read.
Oh, okay. Who's that?
It's me.
Oh, okay.
So, can you? Okay. Okay, let's start. 1.1.2 Sequential Stern-Gerlach experiments. Let us now consider a sequential Stern-Gerlach experiment. Am I audible, right?
Yeah, you're audible.
Yeah. By this, we mean that the atomic beam goes through two or more SG apparatus in sequence. The first arrangement we consider is relatively straightforward. We subject the beam coming out of the oven to the arrangement shown in figure 1.3a, where SG Z hat stands for an apparatus with the inhomogeneous magnetic field in the Z direction or Z direction, as usual. We
Okay,
then
pause.
block,
Sorry,
yeah,
pause. Let's just see the diagram first. So this is 1.3.a. We have an oven. We have SGZ. That's the magnetic field in the Z direction. And then we have another SGZ. So let's read the description now. Sorry to interrupt you. Continue, please.
yeah. So we then block the SZ minus component coming out of the first SGZ apparatus and let the remaining SZ plus component be subjected to another SGZ apparatus. This time there is only one beam component coming out of the second apparatus, just the SZ plus component. This is perhaps not so surprising. After all, if the beam, if yeah, after all, if the atom spins are up, they're expected to remain so, short of any external magnetic field that rotates the spin between the first and the second SGZ apparatus. Says. Should I read more?
Yeah, you can keep going. Up
Yeah.
to you.
A little more interesting is the arrangement shown in the figure 1.3b. So we see the figure, or
Yeah, the figure is visible, right?
yes.
Okay.
Here the first SG apparatus is the same as before, but the second one, SGX hat, has an inhomogeneous magnetic field in the X direction. The SZ plus beams that enters the second apparatus is now split into two components, SX plus component and Sx minus component with equal intensities. How can we explain this? Does it mean that 50% of the atom in Sz beams coming out of the first apparatus Hgz hat are made up of atom characterized by both Sz plus and Sx plus, while the remaining 50% have both Sz plus and Sx minus. It turns out it turns out that such a picture runs into difficulty as we will as will be shown below.
Hmm. Okay. Cool. Okay.
Uh,
Uh,
okay,
you want to continue or do you want to take a break?
okay, okay. Let's read one more paragraph.
Yeah.
We now consider a third step, the arrangement shown in the figure 1.3c, which most dramatically illustrates the peculiarities of quantum mechanical system. This time we add to the arrangement of figure 1.3b yet a third apparatus of SGZ type. It is observed experimentally that two components emerge from the third apparatus, not one. The
Hmm.
emerging beams are seen to have both SZ plus component and SZ minus component. This is a complete surprise because after the atoms emerged from the first apparatus, we made sure that the SZ minus component was completely blocked. How is it possible that the SZ minus component, which we thought we eliminated earlier, reappears? The model in which the atoms entering the third apparatus are visualized to have SZ plus and SZ plus SX plus is clearly unsatisfactory. This example is often used to illustrate that in the quantum mechanics we cannot determine both Sz and Sx simultaneously. More precisely, we can say that the selection of Sx plus beam by the second apparatus SGX hat completely destroys any previous information about Sz. Okay.
Okay. That was interesting. Okay. Um, let's just do a or yeah, I guess we can keep going. Anybody has any questions about what's going on here? Okay, looks like everybody's super smart here. Cool. I don't have any questions either, thankfully. But yeah, this is pretty interesting. That especially the part that even though the SZ minus beam has been blocked here and it's only SZ plus, after the SGX is used and the SGZ is used, we can again get SZ plus and SZ minus. That's kind of wild, to be honest. Okay, cool. Okay, let's keep going. Okay, I'm gonna do some reading now. It is amusing to compare this situation with that of a spinning top in classical mechanics, where the angular momentum L is equal to I omega can be measured by determining the components of the angular velocity omega. By observing how fast the object is spinning in which direction, we can determine omega x, omega y, and omega z simultaneously. The moment of inertia is computable if we know the mass density and the geometric shape of the spinning top, so there is no difficulty in specifying both Lz and Lx in the classical situation. Cool. It is to be clearly understood that the limitation we have encountered in determining Sz and Sx is not due to the incompetence of the experimentalist. True, fair enough. By improving the experimental techniques, we cannot make the Sz minus component out of the third apparatus in figure 1.3 disappear. Yeah. The peculiarities of quantum mechanics are imposed upon us by the experiment itself. The limitation is in fact inherent in microscopic phenomena. Okay. Okay, 1.1.3 Analogy of polarization of light. Okay. I'm gonna offer people a chance again to read. Is somebody gonna take bait?
Hello.
Yes, bro.
Um, hello. I think I can read. I have a few things I want to suggest or point out, maybe.
Yeah, sure. Absolutely.
Um, so I don't know if 1.13 will be helpful for a discussion.
Okay.
This is one of the things I kind of disagree with the book with starting off with classical intuition. I
Hmm.
think it can build bad intuition if we continue. It can give you the wrong picture of quantum mechanics. So
Okay.
I don't know. I mean, I'll continue and read it, but I just want to point that out.
How do you like? What do you mean by it's giving the wrong thing?
So for example, in a spin, I don't think we have enough of the formalism to really understand what's going on, like, even between the diagrams. When you're talking about spin and the experiment, we still might be thinking, people who are new to this might still be thinking of like a particle like going through something and following trajectories and stuff like that.
Right.
Yeah, quantum mechanics gets rid of that completely.
Yeah. Yeah.
We can
Yeah.
only talk about what we see on the detectors, right? So you can only say you prepared it in such state, and then you saw it on the screen being up and down, right?
Hmm.
And then this section I'm about to read relates it to like electric fields and stuff like that. So
Yeah.
yeah, I just want to point that out. I don't know, just
Uh,
I can read it and we can talk about it further once we get deeper into the theory. I think maybe.
yeah.
If-
I mean, like I'm not like, as I said, like I'm not super like good at this stuff. So I'm still learning myself, and I haven't actually read this part, so I'm not sure if it's useful or not. So you guys tell me.
Yeah, actually,
I think,
actually, we can
yeah.
read it and let's understand what's going wrong with it.
Okay, sure.
Okay, that's fair. Okay,
Let's begin. Okay, go ahead.
all right. Because this situation looks so novel, some analogy with a familiar classical situation may be helpful here. To this end, we now digress to consider the polarization of light waves. This analogy will help us develop a mathematical framework for formulating the postulates of quantum mechanics. Consider monochromatic light wave propagating in the z direction. A linearly polarized or plane polarized light with a polarization vector in the x direction, which we call for short an x polarized light, has a space-time dependent electric field oscillating in the x direction. So e to the s. Okay. Likewise, we may consider a y polarized light also propagating in the z direction.
Hmm.
Okay. Polarized light beams of type 1.5 or 1.6 can be obtained by letting an unpolarized light beam go through a Polaroid filter. We call a filter that selects only beam polarized in the x direction an X filter. An X filter, of course, becomes a Y filter when rotated by 90 degrees about the propagation z direction. It is well known that when we let a light beam go through an X filter and subsequently let it impinge on a Y filter, no light beam comes out provided. Of course, we are dealing with 100% efficient Polaroids. See figure 1.4a. The situation is even more interesting if we insert between the X filter and the Y filter yet another Polaroid that selects only a beam polarized in the direction, which we call the X prime direction, that makes an angle of 45 degrees with the X direction in the XY plane. See figure 1.4b. This time, there's a light beam coming out of the Y filter, despite the fact that right after the beam went through the X filter, it did not have any polarization component in the Y direction. In other words, once the X prime filter intervenes and selects the X prime polarized beam, it is immaterial whether the beam was previously X polarized. The selection of the X prime polarized beam by the second Polaroid destroys any previous information on light polarization. Notice that this situation is quite analogous to the situation that we encountered earlier with the Gerlach arrangement of figure 1.3b, provided that the following correspondence is made. So we have z component plus or minus atoms, x, y polarized light, and if other ones, x direction plus or minus atoms, x prime and y prime polarized light. Where the x prime and the y prime axis are defined as in figure 1.5, let us examine how we can quantitatively describe the behavior of 45 degrees polarized beams, X prime and Y prime polarized beams within the framework of classical electrodynamics using figure 1.5 we obtain. Okay.
Some ugly looking equations that
Yeah.
were just not read out loud.
I don't know how many people here are familiar with it though, but
I've seen them before, so good
okay,
enough.
yeah. Okay. In the triple filter arrangement of figure 1.4b, the beam coming out of the first Polaroid is an X hat polarized beam, which can be regarded as a linear combination of an X prime polarized beam and a Y prime polarized beam. The second Polaroid selects the X prime polarized beam, which can in turn be regarded as a linear combination of an X polarized and Y polarized beam. And finally, the third Polaroid selects the Y polarized component.
Okay. Pause for a second. Anybody has any questions up until now? Any doubts, anything to discuss from what we have discussed up until so far? Well, interesting stuff. I mean,
I think I have a comment to add.
yeah, sure.
So basically, few things in quantum mechanics look very strange, and partly because it is strange, and partly because of the like PR attention that quantum mechanics has got over the years. So I think the person who taught me, he always related quantum mechanics to waves, because ultimately quantum mechanics, we will see that it is also described by something called as a wave function. So just I think we can see this part just to make sure that at least few of the things in quantum mechanics is not unique or not like super strange. It kind of shares some properties that we usually see in classical systems, for example, in waves. I think that particular intuition will help in later on, because like there are few properties which is just coincidental. Like it is just you change some h bars and c's, and you get the exact copy of what you get in waves for the quantum mechanics, I think.
Oh, cool.
Can I
So, like-
disagree? I'm sorry.
Go ahead.
Okay, I was gonna say I'm gonna disagree slightly here with the statement about waves. I think it can be helpful intuition for like starting out, but I think it can lead to really bad intuitions and later on more confusion.
Yeah. I mean,
think
you have to. Yeah.
I think the mathematics, sure. I think to be more precise, it'd be like a mathematics of 4-year systems and 4-year analysis. I think that'd be better than just waves. Because for example, if we get to the double slit experiment, thinking about it for one particle as like a wave going through it is fine. But once you start introducing like multi-particle scenarios, then it gets then you get like six-dimensional patterns, and then so it gets worse from there.
Yeah. I mean, obviously, at some time you have to make that distinction. Okay, this is classical, this is quantum, but just to make sure, I mean, my idea was just to soften that jump, because I mean, quantum mechanics initially feels like a very big jump. The way we think about things, the way we think about physics before coming to quantum mechanics is like very different. Like you said, like trajectories, particles, moving things here and then. That is not how quantum mechanics work. So I think in that sense, I mean, after a while, when you're introduced to the full formalism of quantum mechanics, you will start seeing things in that way. So then all these classical analogies that we have built is eventually we have to grow out of it.
Yeah. Okay. Yeah, I completely agree. Yeah.
Cool. Okay. I had a question, but I forgot what it was because like the conversation went elsewhere. But anyway, great. I think that was some great comments. Okay, where were we? Finished this, right? Finally, the third Polaroid selects the Y polarized system, polarized component. Okay. Okay. Who was reading?
I can continue.
Yeah, you want to continue? Cool.
Okay. So I think we're at page 8, right? If I'm not mistaken.
Yeah.
Okay.
Applying correspondence.
Yeah. Okay. Applying correspondence 1.7 from the sequential Stern-Gerlach experiment of figure 1.3c to the triple filter experiment of figure 1.4b suggests that we might be able to represent this spin state of a silver atom by some kind of vector in a new kind of two-dimensional vector space. An abstract vector space not to be confused with the usual two-dimensional xy space. Just as x hat and y hat in 1.8 are the base vectors used to decompose the polarization vector x hat prime of the x hat prime polarized light, it is reasonable to represent the spin in the x direction plus state by a vector, which we call a ket in a Dirac notation to be developed fully in the next section. We denote this vector by a mathematical thing and write it as a linear combination of two base vectors, such and such, which correspond to the spin in the z direction plus and the z direction in the negative state, respectively. So we made conjecture, and so
These two equations.
yeah,
Okay.
which will be explained in the later sections. In an analogy with 1.8, later we will show how to obtain these expressions using the general formalism of quantum mechanics. Thus, to be unblocked to the unblocked components coming out of the second x hat apparatus of figure 1.3c, it is to be regarded as a superposition of z plus and z minus in the sense of 1.9a. It is for this reason that the two components emerge from this third z hat apparatus. The next question of immediate concern is how are we going to represent the y plus and minus states? Symmetry arguments suggest that if we observe a z plus or minus beam going in the x direction and subjected to any y hat apparatus, the resulting situation will be very similar to the case where a z plus or minus beam going in the y direction is subjected to a x hat apparatus. The kets for y plus or minus should be then regarded as a linear combination of z components, but it appears from 1.9 that we have already used up the available possibilities in writing x components. How can our vector space formalism distinguish from y states from x states? An analogy with polarized light, again, Rescue says here. This time we consider a circularly polarized beam of light, which can be obtained by letting a linearly polarized light pass through a quarter wave plate. When we pass such a circularly polarized light through an X filter or Y filter, we again obtain either an X polarized beam or a Y polarized beam of equal intensity. Yeah, everybody knows that the circularly polarized light is totally different from the 45 degrees linearly polarized X prime polarized or Y polarized light. Mathematically, how do we represent a circularly polarized light? A right circularly polarized light is nothing more than a linear combination of an X polarized light and a Y polarized light, where the oscillation of the electric field for the Y polarized component is 90 degrees out of phase with that of the X polarized component.
Okay. Okay.
Yeah.
Cool. You want to take a break or you want to continue?
I can continue, it's fine. Until the end of the section, it's fine, yeah.
Just one thing.
Yeah.
Actually, okay, so this is the equation for circularly polarized light, right?
Yeah.
Okay. Okay.
One of them is just an out of phase component, yeah.
Right. Yeah, that's what I was thinking.
I think this is trying to build up the intuition behind why we need complex numbers for new vector space. Yeah.
Okay.
Yeah. All right. It is more elegant to use complex notation by introducing epsilon as follows. Real epsilon equals E over E naught. For a right circularly polarized light, we can write epsilon equals this expression. Where we've used I equals I to the pi divided by 2. We can make the following analogy with the spin states of silver atoms. That gives you that. Applying this analogy to 1.12, we see that if we are allowed to make the coefficients preceding base Ketz complex, there is no difficulty in accommodating the y directions atoms in our vector space formalism. Vector equation, which are obviously different from 1.9. We thus see that the two-dimensional vector space needed to describe the spin states of silver atoms must be a complex vector space. An arbitrary vector in the vector space is written as a linear combination of the base vectors, z components, with, in general, complex coefficients. The fact that the necessity of complex numbers is already apparent in such an elementary example is rather remarkable. The reader must have noted by this time that we have deliberately avoided talking about photons. In other words, we have completely ignored the quantum aspect of light, nor did we mention the polarization states of individual photons. This analogy we worked out is between Ketz and an abstract vector space that describes the spin states of individual atoms with the polarization vectors of the classical electromagnetic field. Actually, we could have made the analogy even more vivid by introducing the photon concept and talking about the probability of finding a singularly polarized photon in a linearly polarized state, and so forth. However, that is not needed here. Without doing so, we have already accomplished the main goal of this section, to introduce the idea of quantum mechanical states are to be represented by vectors in an abstract complex vector space. Finally, before outlining the mathematical formalism of quantum mechanics, we remarked by the physics of a certain Gerlach apparatus is far more than simply academic interest. The ability to separate spin states of atoms has tremendous practical interest as well. Figure 1.6 shows the use of the Stern Gerlach technique to analyze the results of spin manipulation in an atomic beam of cesium atoms. The only stable isotope of this alkali atom has a nuclear spin of 7/2, and the experiment sorts out the F=4 hyperfine magnetic substate, giving 9 spin orientations. This is only one of the many examples where this once mysterious effect is used for practical devices. Of course, all of these uses only go to firmly establish this effect and the quantum mechanical principles, which we will now present and further develop.
Okay. We're gonna stop here, and I actually have a question. If anyone can answer, how the heck where did we get this equation from 1.12? I did not understand that. Anyone? I'm just gonna write it down. If anyone has any other questions, go ahead. Hopefully somebody will answer yours. Until then, I'll write mine.
I mean, it is just, the way we do is, for example, this equation, I think it comes from equation 1.10.
Okay.
So it's like, I think everybody is familiar with the Euler's formula, right? E power I theta is equals to cos theta plus I sin theta, right?
Yeah.
Yeah. So basically, we write complex numbers. We work with complex numbers, and then whenever we have to relate, we just take the real part. So I think if you take the real part of 1.12, you will exactly get 1.10. If I am not wrong.
Yeah, that's right. Yeah.
Okay. Why is it saying I equals to e to the power of I pi over 2?
Because if you put e power I pi by 2, it is like cos pi by 2 plus I sin pi by 2, right?
Okay. Right.
Then cos pi by 2 is 0. Yeah, cos pi by 2 is 0 and sin pi by 2 is 1. It is exactly I.
Okay.
Just using the Euler's formula.
Right. This is page 32.
And there is a very subtle flaw with this notation that when I read in my first year. So whenever you have this formalism of taking real parts, you cannot multiply two things, because when we have complex numbers, so real part of z1, where z1 and z2 are complex numbers, real part of z1 plus z2 is equals to real part of z1 plus real part of z2. However, real part of z1 multiply z2 is not equals to real part of z1 multiply real part of z2. So you should be careful if you are multiplying things. You take the real part before, multiply, and then take the real part afterwards. If you just multiply and then afterwards you take the real part, you are going to get a mess.
Right. Okay.
I think multiplication is not required for the most part. If I remember correctly.
Okay. So, you read this book then, the whole thing?
No, actually, in my time, it was my instructor taught it with his notes. I can share his note also if it is available still. I was taught mostly with graphics. Griffiths.
Oh,
We did not read this book, so it is
right,
little
right, right.
bit new for me.
I used
So that
Griffiths. That was for undergraduate. Uh, undergraduate course in quantum mechanics.
Yeah. So we were taught quantum mechanics in third year when I was in third year
Yeah.
undergraduate. So I
Right, right.
think at that time that was appropriate, maybe.
Yeah, true. All right, cool. Uh, yeah, somebody had something to say.
I was gonna say I read this book. I read some of it. I took a
Okay.
course. I wasn't. I went from Griffiths to this book. So second year I took Griffiths, and then third year I would took this, and the jump was too much for me.
Oh.
So that's why I want to warn people of like bad intuitions because that's kind of it kind of it made it more difficult to learn
Hmm.
it. Because if Griffiths he says some things that are kind of wrong
Hmm.
or just too simple and it gives you the wrong idea,
Hmm.
and then when then you once you
Yeah,
take like a graduate course,
I
you
mean
get slapped in the face by this formalism.
yeah, I mean Griffiths is I mean I hate Griffiths. I mean if we have seen the I mean if you see the contents, he just in the chapter 2 he just blatantly just puts all the mathematics. You have this 1D oscillator, 1D box, 2D box, and then finite box, and then at the third chapter he will introduce the formalism. I mean, what sort of logic is this? You are just
Yeah.
giving the results in the second chapter, and you are setting up the formalism in the third chapter. When I read, I completely found this completely atrocious. I mean, how is this? How does it work? I mean, the way we do physics is we lay down the foundation, we discuss the mathematics, and then we start doing the examples. He does it completely opposite. I mean,
Yeah. Yeah, yeah, this formalism is definitely weird. But I think this book we're reading is technically is the best one, I guess. It's not too mathematically complex, but also just good enough. Because there are other ones that are really hard to understand.
Cool. Okay. Um. Yeah. Okay. So, guys, from what I've seen, this 1.2 gets bras and operators. This is like the next topic. So, we're not gonna do it in this class because, like, I think we're almost, or I guess we have like 20-15 minutes. Um, you guys want to do? You guys want to continue? What do you guys think?
Yeah, actually, we can continue.
All right.
We
Let's
can do
con-
1.2 or like 1.211.
Yeah. Okay. You want to read?
Yeah, I can read.
All right. Perfect. Start from 1.2.
Yeah. So in the preceding section, we showed how analysis of the Stern-Gerlach experiment led us to consider a complex vector space. In this and the following section, we formulate the basic mathematics of vector spaces as used in quantum mechanics. Our notation throughout this book is the bra and get notation developed by P.A.M. Dirac. The theory of linear vector spaces had, of course, been known to mathematicians prior to the birth of quantum mechanics. But Dirac's way of introducing vector spaces has many advantages, especially from the physicist's point of view.
Hmm.
So we consider a complex vector space whose dimensionality is specified according to the nature of a physical system under consideration. In Stern-Gerlach type experiments, where the only quantum mechanical degree of freedom is the spin of an atom, the dimensionality is determined by the number of alternative paths the atoms can follow when subjected to an SG apparatus. That's the Stern-Gerlach apparatus. In the case of the silver atoms of the previous section, the dimensionality is just 2, corresponding to the two values SZ can assume. That's positive and negative.
Hmm.
Later in the section 1.6, we consider the case of continuous spectra. For example, the position coordinate or momentum of a particle, where the number of alternatives is non-linear. What is non-denumerably infinite? What does that mean?
I'm guessing that it is not countable. Like Infinite number of values, something like that.
It's just an adjective, I suppose.
It means it's uncountably infinite. So like, uh, that means you can make like a one-to-one correlation with the natural numbers.
Oh,
Okay.
Yeah. So like, if the natural numbers are called countably infinite, and like the real numbers are called uncountably infinite. Non-denumerably is just like another fancy word for that.
okay.
Okay, got it.
It's done.
Yeah. So, in which case, the vector space is question is known as a Hilbert space after D. Hilbert, who studied vector spaces in infinite dimensions. In quantum mechanics, a physical state, for example, a silver atom with a definite spin orientation, is represented by a state vector in a complex vector space. Following Dirac, we call such a vector a ket and denoted by alpha. This state ket is postulated to contain complete formation about the physical state. Everything we are allowed to ask about the state is contained in the ket. Two kets can be added. Alpha and beta, alpha plus beta is equals to gamma. So the sum gamma is just another ket. If we multiply alpha by a complex known as C, the resulting product C alpha is another ket. The number C can stand on the left or on the right of a ket. It makes no difference. In in the particular case where C is zero, the resulting ket is said to be a null ket. That's obvious, I suppose. One of the physics postulates is that alpha and C alpha, with C being non-zero, represent the same physical state in other words, only the direction in vector space is of significance. Mathematicians may prefer to say that we are here dealing with rays rather than vectors. And observable such as yeah.
Yeah. Um, cool statement. Mathematicians may prefer to say that we are here dealing with rays rather than vectors. Okay. I'm just gonna write some of this down. Anybody has any questions, comments, doubts? Please speak up or hold your silence.
I have a comment on the ray thing.
Yeah.
I think the reason why they pointed it out is because I don't know why he didn't point this out. You can multiply a cat by e to like I theta,
Okay.
and it's basically like a transformation. And it spits out the same cat. So we only worried about classes of cats, because if not, you're gonna get like a bunch of the same cats representing the same physical system. So all the cats are the same up to a transformation, and those are the ones that are physically significant.
Oh, okay.
Yeah.
I think the way I understood it, I mean, we are, I think, very shortly going to introduce with this. Uh, forgot the name. I think so. We are going to be introduced with, so in quantum mechanics, whatever we measure is a probability. So probability is the mod squared, like the ket and multiplied with its conjugate. So when you are taking a conjugate, so that e power whatever thing is there, that gets nullified, right? Because e power I whatever multiplied by e power minus I is just going to get annihilated. So that phase part, so whatever e power is there, we call it the phase. So phase part actually do not contribute to the probability, and ultimately we are going to normalize things. So when we are normalizing that, whatever that c times of cat, whatever that is, that immediately gets washed away, because if it is c, we will eventually divide by c. If it is 2c, we will eventually divide by 2c. So then those constants actually take care of themselves. We are more interested about what is the vector itself. So I think just on the perspective to look.
Cool. Okay. All right. Let's continue. Who was reading?
Yeah.
Yeah. Go ahead.
Yes, I was reading. Yeah. So actually,
And observable.
yeah, an observable such as momentum and spin components can be represented by an operator such as A in the vector space in question. Quite generally, an operator acts on a ket from the left. So that may be like in general how we put it, which is yet another ket. There will be more on multiplication operations later. In general, A alpha is not a constant times alpha. However, there are particular kets of importance. such as eigenkets of operator A, denoted by A prime, A double prime, A triple prime, and so on, with the property A prime is equals to A into A prime is equals to A prime into A prime.
A
And
prime get A prime.
yeah,
Like this is
how's
K prime.
I do not understand this.
So
Like,
what what's your
it's
conclusion?
just means like the capital A is the denote like we denote it with capital A, I suppose.
So the capital A is the observable or the operator. Sorry, operator.
Yeah.
Capital A is the operator. Then we have the ket A prime, and for eigenkets such as ket A prime, we have that when the operator acts on the like from the left on the ket A prime, we get the eigenket, the eigenvalue, and
Yeah.
the ket itself. That's what
Okay.
I.
Okay.
Yeah,
That's a
just to make a
property.
comment. Yeah,
Yeah.
uh, yeah. So just to make a comment. So when we have like all these things, I mean, it is easier to visualize just as a matrix. So A is a straight vector. I mean, just a column vector, one, two, three, whatever. Then A becomes your matrix. So in matrix, we are always already familiar with eigenvalues, eigenvectors, all those things. So then we can sort of relate it with
Yeah.
A becomes the matrix. Alpha is the straight vector for which these a primes, the small a primes are the eigenvalues. So in quantum mechanics, when we are measuring something, we have a operator that will act upon some vector to produce some eigenvalue and multiply by the same eigenvector. So that observable that we are going to measure, that is the eigenvalue. So I think everybody would be familiar with the Schrodinger's equation, right? So we have some bunch of things on the left hand side, and then we have the psi, and then we have E, capital E, and then psi. So that is just a Hamiltonian operator. Like we want to measure the energy, so we have this Hamiltonian operator. We can just write capital H psi is equals to E psi. So that is the way. All the operators will follow that same regimen. Like we have some operator straight vector, the observable will come out as the eigenvalue and then that same vector. So this is just a formalism.
Okay. Cool.
Derek,
Uh, yeah. Go ahead.
so A prime here, this is acting as a ket and as a number. I don't get how can we do
No,
this here?
no. It is just to make track. So the number is just a prime. You can use the same thing in between. You can use the same thing for denoting the eigenvector and the eigenvalue. So when we write a prime in the ket, that is representing a vector. When we write just a prime, that is a number, a complex number in general. So it is like a prime will give us that the same the same notational number and understand in that way.
So like A prime as in the ket is like A B, so it would be like A plus BI there, and then A dash here is just A plus BI.
Yeah, a prime, the thing that we're seeing on the left of a prime ket, that is just a complex number. That is our observable.
Okay. And then A prime.
Wait, I'm sorry. Complex number? I thought it should be a real number.
Yeah. I think
Oh,
we.
yeah. Okay,
The
sorry,
outcome.
yeah.
Yeah.
Observables are always real, yes. Just sorry.
Yeah.
Observables are
They're
always
like,
real, yes. This A, sorry, this components of A, the components of the matrix A will be complex number, right? It maybe in general maybe a complex number. I think that is the way it works. Yes, all the variables are always real, and then we are going to formulate, put those condition on that, and then we will have a special kind of matrix. So not all matrices form, or not all matrices are are operators. We have a specific kind of matrices which actually can be referred to as operators. I mean, I think we will read all those things later.
Okay, cool. One question, if anybody can answer. So in equation 1.17, it says that A dot ket alpha equals to A alpha. So dimensions wise, when we consider them as matrices, it will be like m by n and n by 1, right? And the final matrix A ket alpha will be m by 1. So what would that represent? Like how, what does it mean that it acts on the ket? What does that mean?
I mean, it is just a simple multiplication. You have, I mean, let's suppose we are working in 3 dimension, like most
Yeah.
likely we will. So then A will be a 3 cross 3 matrix. A alpha will be like 1 cross 3, like 1 2 3, like 1 2 3
Yeah.
this vector, and then it will become 1 2 3, like 3 cross 3 multiplied by 1 3 cross 1. Then you will get 3 cross 1. If that is making sense.
So the operator has to be a square matrix always?
Yes. Yes.
Why?
As far as
Maybe I
uh,
can explain. So
yeah, yeah.
operator are transforms. They can be matrices. That's a simple thing. They can be finite matrices, square matrices, like the one you see. But they can be also other stuff. So they can be basically integrals. They can be derivatives. There are many ways to represent the same operator, roughly speaking. So which
Okay.
is basically means that the operator is a transformation part. The vectors are typically the states in this scenario, and then you transform one state to another state with a transformation. And let's say the operators are the brass, the dual, and the vectors instead are the states, which are the cats. So you basically transform from one cat to another cat through a transformation operator. Transformation operator can be maybe a rotation, can be maybe a spin operator, can be maybe also an evolution operator. That you transform, you move one cat over time and you transform it into an operator. When you basically have a system, simple system like spin, okay, these are basically, let's say, three-dimensional matrices, okay, let's say very simple, you can imagine as a 3 by 3 matrix, a spin.
Hmm.
In the case of derivatives, integrals, in the case of movement, Fouriers, and so on, these are infinite dimensional matrices. It means basically matrices with an infinite number of lines and columns, but still square. And that's the kind of, let's say, abuse of mathematics, because infinite matrices are kind of bad for, let's say, they're not well defined mathematically. But it's a kind of way to say, okay, from the kind of finite matrices, you extend to infinite matrices, you extend to real operators. And that's a kind of different way to represent operators. There are many ways to represent states, and there are many ways to represent operators. And then in the case of states, for example, you can represent the state as a vector, kind of a three vectors. You can represent the state an infinite vector, like imagine a wave function is a kind of infinite vector. You can represent the same mathematics as a wave functions, which means more or less that instead of having a space of states, a space of vectors, you have a space of functions. Okay, and this means all these states are represented either as functions or as vectors. And then in the different scenarios, you basically can represent in multiple ways, and there are duals, which are operators. So there is more or less a vector, and a dual is a matrix. A function, a dual is a let's say, a derivative operator, or a vector, a dual is an integral operator. So there are many ways. So it's basically what one is the linear part, these are linear operators, and the other side are basically vectors. So the linearity principle always apply, whether it's a vector or matrices. And then in the middle, there is this product between, let's say, vectors and vectors, operators and operators. There is a way to define a geometric product, roughly speaking. Which, when you combine the bra and the cat together, you basically see that the bra and cat together gives out numbers.
Right. Okay. 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 I understood. Like,
But just go on. Just go.
makes sense. So, like, to some extent. Okay. Cool. Where were
You will
we?
need some. I was preparing some slide on Fourier. And in the Fourier case, it's kind of simple. You can have a very simple version of this, and you see it more in a concrete manner. So you need to see basically with some matrices and play around with some matrices and such.
Okay.
Yeah, I mean, I just have a cross question. If I'm not wrong, you said, if I heard it right, so for kits, the dual for kits is a matrix.
Is a bra. So the cat
So
is a
bra,
state and the bra is an operator. There are different representation of operators, which can be matrices, which can be differential operators, which
so
can
I
be
mean,
integral operator.
yeah, so that part I don't understand. Bra is just a dual. I mean, when we have uh, a vector that comes from a vector space, so then bra will come from the dual vector space, right?
No, there is a dual space, which is a space of operators.
No, no, I'm just talking
The
about
dual
the state, the only the state vectors, the alphas.
Yeah, the state vector will live in a state space. Okay. The dual
Yes,
space
yes,
is an operator space, is a matrix
yeah,
space, or is
yeah, yeah.
a
I mean, yeah, yeah. So I mean, bras are the dual to the state vectors, right?
yeah, but they are operators.
Okay.
So
Okay,
the
so I
dual
used to
space is
think
not a
is
space of the dual space is
uh,
no longer states, it's operators.
yeah, yeah. Okay.
So which is in the case of matrices, roughly speaking, the state is represented by vectors and the represented by matrices. Okay. In the case of functions, basically, more or less, the states are represented by functions, which are the kind of wave functions, and then the operators will be differential operator, which are kind of evolution operator with some derivatives and such. Okay. That's
Yeah.
more or less a simple example. There is another equivalent, which are linear operator, which are integral operator, which are also another way to represent operators.
Oh,
Yeah.
yeah.
So in practice, you're talking about representing operators in many ways, represent states in many ways, and every time to one representation of states, there is a dual representation of operators.
Okay. Okay. Yeah. I understand. I understand. Yes.
And
Yes.
then there
I
is, roughly
understand. Why?
speaking, a treatment where we work only with states. There is a treatment where you can work only with states and forget the operators become dumb, roughly speaking. And there's the opposite treatment where you work only with operators and the states
Yes.
become dumb.
Yeah.
Which is the second one is whatever you call matrix mechanics from Heisenberg. And the first one
Yeah.
instead is wave mechanics from Schrödinger.
Yes. Heisenberg we will study probably later. We start with Schrodinger's, I
This
think.
means in the world of is important. That was a comment of IC, basically, of the guy, of the guy on the other side, was practically in the historical manner of learning it. Okay, you learn always with, okay, I give you a differential equation, that's Schrödinger, fine. Then you solve it, one particle, one coordinate, boom, and you start to solve it. Okay, that's a kind of historical way to teach it. What is
Yeah.
the more modern way to teach it is to tell that there is this bracket thingy, and it's practically, you already see it basically in the work of a book of Dirac, for example. He starts with brackets. He doesn't explain that bra can be multiple things and cat can be multiple things. He explains it later.
Mm. Okay.
Why? Because
Thank you
more or
very
less there
much.
is a kind of a geometric thing in the middle happening. The
Yeah.
geometric
Yeah.
thing in the middle happening is something like projected geometry. Have you ever seen projected geometry, any of you?
Yeah. I have studied a little bit. I think in quantum information
Projected
theories and all, they use this.
geometry.
Yeah. I mean, this is
Yeah,
this.
yeah.
This.
In
I
quantum
mean,
information, you can do similar things.
yeah. In quantum information theory and this in decoherence, they talk about this row thing and then projection operators. There is just
It's what?
completely one-to-one correspondence. There is. I mean, there is this row. I don't remember what is. I think that is the state, and then you have this projection operators.
I think it's a density. Yeah, okay,
Huh?
but that's a density. But then I don't know exactly what you refer to. I think that's a density, but that's a different thing.
Yeah. Exactly.
The first thing to
The density
okay,
operator.
the first thing to get
That is just
the first thing to get
yeah
right. Yeah,
yeah
the first example to get right is more or less the following: in projective geometry, okay, there are essentially lines on one side and points on the other side. Okay,
Okay.
points are basically, let's say, individual points, and lines that are more or less lines to the infinity. Okay, and there is this duality between line and points. Okay, then the same duality you can be again in projective geometry. You can present a line with a matrix, which becomes a transformation, and a point with a vector, which is a state. Okay, this is an expanded version of the same projective geometry duality, which becomes operator on the left and vectors on the right. Vectors are as not necessarily matrices. Vectors can be in different type of space. If the space is a space of functions, you will have a bunch of agent modes and agent values, which are functions. If the space of vectors is basically, let's say, matrices, you will have more or less what you have the coordinate axis in a matrix system.
Okay.
So in a space of matrices, basically you always can rotate the matrix and put in a diagonalize it. Basically simplify it. Okay, out of this matrix, there are 3 fundamental vectors, and there are basically a bunch of numbers attached to it. In a space of functions, you can more or less do the similar thing. It's okay, out of this differential operator, in this case, maybe my Schrödinger equation, roughly speaking, out of this, there will be an infinite number of possible states, which are my imaginary harmonic oscillator states. And out of those, there will be basically a bunch of fundamental numbers, which are the energies.
Okay.
Which means, again, you'll get back H, which is the Hamiltonian, multiplied by the state, by the ket in this case, equal energy, which is the eigenvalue, multiply again by the ket, which is an eigenvalue equation for the energy. Same thing, you can say, okay, for the spin, LC is now is a matrix which is 3 by 3, multiplied by a vector, equal a number which is my angular momentum, multiply again by the ket, which is a vector, which is my free matrix vector, basically to represent just the spin.
Yeah.
So according to the variable, you end up in a different space, and that space of variable have their own rules with their own objects. And then in that thing, you try to apply a linear operator theory, which tells you that basically there is always a way to decompose the space in a set of fundamental cases. When you do
Yes.
the color of the light, more or less you do a similar thing. You say, okay, I want to decompose the light in colors. My colors are roughly my eigenstates. The amount of color is basically the eigenvalue, and the operator on the left is essentially a Fourier transform.
Yeah. Okay. Cool.
Okay. That was a lot of information and I did not get
Yeah.
it.
But it's important that you go back and back and back. So which is basically restart from scratch. Yeah.
Mm.
Yeah. I don't know. Yeah. You need to get it back multiple times. That's why it's important. Probably you go back to the book and restart basically from the book and reread through the book again. You follow? Don't try to understand it in one go. Try to understand. Okay, but there is this concept of transformation and vectors, and then re-go through it multiple times, and then you start to. Oh, but this one, in this case, realize it in one way. In the other case, is realize it in another way.
Okay, cool. Cool. Okay. I hope whatever the question was last has been answered. I think we're gonna stop here. We finish up until the equation 1.19. So I'm just gonna write that down. Anybody else has anything else to say, suggest, doubts, comments, anything? Okay, I will take that as a no. I think the class went cool. I had fun, definitely.
The recording. There is a recording of the first part. You have a recording of the first part is available, right?
Yeah, we're recording the whole session. We'll probably
cool.
upload it. Yeah. So yeah, that's not an issue. Okay. I think we're good for the day. Glad this happened again. I had fun and I learned a lot of stuff. So, and I hope you guys did as well. I'm gonna leave the philosophy for next time. But
maybe you can try to reread through other books. So, which is try to go to the same chapter, imagine of Dirac, or the same chapter of maybe another book, and try to reread it in different manners. That's another way that you can start to get it through.
Okay, that's a good idea. Yeah, we can work on that. Maybe like we can use Shankar or something.
Yeah. I
Yeah,
was just going
Shankar
to
is
mention
one
that.
part, one example, but you can compare it
Yeah.
with the Dirac. But then you need to open the same exact topic and try to read it across multiple books, and then you start to see basically that it behaves differently.
Okay. We'll try. Like,
Actually, I will prefer Shankar only.
okay.
Yeah, okay.
So
It
we can go
depends
with
on the
that.
style of study. So if people prefer Shankar only, but so that's also a type of studying. So it depends on you guys, basically. So each one of you actually how they prefers. What you learn is a
Actually, I think it will be
connectivity.
easy to go with that, but like
Yeah.
it will be easier to go with.
Okay. Yeah.
Typically, what remains is the connectivity between the concepts. You forget the single concept that after a couple of years, but remains a connectivity across the multiple concepts.
True. Okay. Yeah, so that's a good idea. We're gonna read from Shankar next time and like go through the stuff once we have completed this part of the topic, I suppose, because that would otherwise it would be a little bit weird. But anyways, we'll figure that out. Anyone else? Anything you guys need to say?
I wanted to try to do. I was preparing the slide deck basically on the optics. Basically, there is a similar thing between matrix and vectors, but applied in the world of optics. Okay, and that is kind of pedagogical, basically, to what you see here, roughly speaking. And that's maybe I can try to finish up the slide and see how it goes.
You want to do the slides like right now or next time?
No, next time. So we do it maybe in 1 week or two because I need to finish off the slide and a bunch of things.
If people are interested, I am
And then-
down for that. I don't mind.
And then I split it in 7 lectures actually because I asked Claude to split it off. But every time I ask Claude something, it takes me 5 hours to ask the next one. It's getting slow. But I split it in 7 lectures, and there is basically So if you remember the initial slide is kind of, let's say, multiple chapters, and now it's 1 chapter per lecture, roughly speaking. And there, the concept is more or less this: the optical device is a transformation. The vector instead is the position of light. And then you transform the position of light to the optical device and transform and move the position of light. The position of light is represented as a vector. The optical transformation is represented as a matrix. And then when you want to have a ray that comes in one way and then gets another way, it's transformed by a matrix, which is by an optical component. It's the same thing, but in a world of rays and basically optical components. And you can imagine this also in the scope of quantum mechanics. You have a piece of light beam, okay? There is more or less an atom that is kind of a scattering. That's the transformation part. And then there's outgoing light beams. And basically that's the out part. It's again a ray transformed by the scattering into another ray.
Okay. I'll have to read up on this stuff. I'm like not very in tune with it, but sounds cool. We can discuss it. You should probably ask Zenith if you can do like another session. Like you can set it up, right?
Yeah, no, we do it definitely on a Friday, maybe this Friday or next Friday, but yes.
Cool. So yeah, you guys can.
And then we try to split it off. We split it off. So basically, we split it in multiple pieces, probably.
Okay. Cool. Yeah, that's fine. We're gonna keep the Sundays for group study though.
Yeah, sure. That's what's the point. The point is the Sunday keep it as is because it's well nice.
Right.
And then the Fridays we try to introduce some side by side, some shape of lecture stuff, or some shape of complementary material or things.
Sure. That's great. Okay. Awesome. Okay. So I guess that's about it for today. Thank you guys for coming. I am glad you guys came. I learned stuff. I hope you all learned stuff. And let's meet again next time and continue with the wherever we left off after 1.1.9, the EigenKit stuff. Okay. Thank you and bye bye.
Bye bye.